All right, so this is a try saying that 10 times fast, a real world problem based on radioactive decay, okay? And our situation is this. An isotope of carbon begins with a mass of 100 grams, and after 1,000 years, it has a mass of 75 grams. Its decay can be modeled by the equation m equals a e to the kt, where t is time in years, k is a constant. Okay, we need to solve for k to be able to write the equation. So we need to write an equation to model the situation. Okay, so we know what a is. So a, remember, is our initial value. We say that it begins with a mass of 100 grams. So I know already that my equation should look something like this. It should be m equals 100 e kt. However, I need to know what k is first. And we would normally not be able to solve that, but it has given us a point. This, at 1,000 years, there's a mass of 75 grams. So we can solve for k actually by plugging in 1,000 for t and 75 for m, and we are able to actually solve for what k is. So that's what we're going to do. So to begin, we need to solve for k. So I know that so my m, this point for m is 75 equals 100 e to, and now my t is 1,000, so I have e to the 1,000 k. Okay, so I need to start solving for this, okay? And this is just like our practice problems. Now we have we have the thing that we are looking for in an exponent, so we are going to have to use a logarithm to help us solve for that. So I'm going to start off by dividing my 75 over 100. Okay, this becomes 3/4, or 0.75. I'm going to write it as just 0.75. Okay, so it becomes 0.75 equals e to the 1,000 k. Okay, so once I get to here, now I have a choice. So normally I could use a log to move this out in front, but I know that to cancel out an e, remember that logarithms and exponential functions are opposites of each other. Since this is base e this is an exponent with base e, I can say if I take the natural log, which is also base e, those things will cancel out. Okay, so this will come with practice. When you see an e, you want to take the natural log, or the ln. Okay, so to do that, I'm going to introduce an ln to both sides. So I'm going to say now that this 0.75 equals e to the 1,000 k, I'm going to introduce ln to both sides. So I'm going to say I'm going to take the natural log of both sides. So this is ln 0.75, this is ln of e to the 1,000 k. Okay, once I get to here, ln of 0.75 is a number. We can calculate that. I'm not going to do that just yet. On this side, I know now that this ln and this e cancel out. They cancel each other out. They just take each other away. So I'm going to erase them. So the ln, they cancel out. They cancel out. I am left with just 1,000 k. This 1,000 k is no longer, that is no longer an exponent. So now it is just on the bottom. So now we have 1,000 k. Okay, ln of 0.75 equals 1,000 k. We're trying to get k by itself, so since it's 1,000 times k, we're just going to divide by 1,000. Okay, so I'm going to divide both sides by 1,000. I'm going to rewrite my k here. So this ln of 0.75 over 1,000 equals k. If you put that into your calculator, ln of 0.75 divided by 1,000, so that is negative 0.00029. Okay, so that is my k. So now I have solved for k, which means that I can write an equation to model the situation. I know what k is, it's over here. So now I'm going to say that my equation can be modeled by m, or the situation can be modeled by the equation m equals 100 e. K is negative 0.00029, negative 0.00029 t. That is my equation to model this. Okay, this would give me the amount of carbon that is left over after any number of years. Okay. Now that was step 1. For step 2, we are going to say after how many years will there be 50 grams? So, or basically, you can think of after how many years will my amount be cut in half. Okay. So doing that, I now have my equation. I know the amount that I'm looking for and I don't know the time, so I'm going to plug this 50 in for m and I'm going to be solving for t. So I'm going to do that. I'm going to say that my m is 50 and it is equal to 100 e to the negative 0.00029t. I'm going to begin working from there. So I know that 50, so I'm going to move this, divide by 100, divide both sides by 100. 50 divided by 100 is just 1/2. So I'm going to take my 100 away since I'm dividing it. And I'm going to say that now this is 0.5 equals e to the whatever. Just like earlier, I have same thing as we did up here. I now have my variable and my exponent. Okay, I need to find a way to move it down. Since I have a base of e, what I'm going to do is take the natural log. Okay, so I'm going to take the natural log of both sides because the natural log will cancel out with this e. And what we're going to do is we're going to say that it's ln of 0.5. So I'm taking the natural log of both sides equals ln of e to the negative 0.00029t. Okay, once I get to here, my ln and my e cancel out, so I'm just left with this negative 0.00029. Sorry, so let me write that again. So I have ln of 0.5 equals negative 0.00029t. And just like earlier, I now have t by itself on the bottom, well, almost by itself on the bottom. So I'm going to divide both sides by negative 0.00029. And this is going to give me something equal to t. When we put this into our calculator, this ln of 0.5, let's check that. So we have ln of 0.5 divided by negative 0.00029 gives us 2,390.16. So our answer to this question is, after how many years will there be 50 grams? We have solved for t by using logarithms and plugging in that 50 grams at the start. And we know that after 2,390 years and a little bit more, that there will be 50 grams left of this isotope of carbon. Okay, so this is how you would use logs to help you solve both model equations and then solve them at the end. Okay, so hopefully this will help you with the last two questions on the worksheet.